Good evening, sir. My name is Matsiko Ian Sezi from Group 7 of the evening class. Our topic is explainable semantic graph convolution networks for facial microexpression detection. I'll be taking you through our machine learning methodology, the machine learning models we used, simulation results, related work, research contributions, and quickly I'll take you through our code for implementing explainability. Then my colleagues will take you through the rest of the code. So to begin with, this is a visualization of our methodology. We started by downloading the FER 2013 dataset, which is a standard dataset available on the internet. Our link to the dataset is provided. So after getting the images, we carried out image normalization, then we resized them, then we expanded the dimensions in order for them to be easily picked out by the graph convolution network, and then we converted the label to a cut matrix for it to be easily read by our GradCam, which we use for explainability, and the SGCN architecture. And then so when after being mapped out, they are fed into the semantic graph convolution neural network architecture, which classifies them as shown in the yellow circle. And then finally we also implemented explainability. So we were able to build 6 machine learning models, 2 of which were graph convolution neural networks, then a convolution neural network, a recurrent neural network, a decision tree, and a random forest. And these different models performed as indicated here. In this table, the second graph convolution network, which only uses ResNet architecture, is not indicated because it had a slightly low accuracy. But we indicated one which employs both ResNet and LeNet, and it gave us a very high and a very nice accuracy. So from the related work, different people have carried out studies on microexpressions in machine learning and deep learning. However, most of these do not go ahead to implement explainability, and also some of them don't focus on the underlying muscles which bring out the microexpressions that we are interested in. They only focus on the superficial expression. So here I'll quickly take you through our code for implementing GradCam for explainability. We started by installing TF-Explain, which is the underlying architecture for GradCam, and then we loaded our trained model. After training it, we uploaded it on Google Drive, and then here, so this code is able to access it, and then we feed an image into it from Google Drive, an image from our dataset. Then it pre-processes it and then classifies it and then prints out a heat map that shows us the features it considered to classify it as it does. So here is an example of 7 images that it classified from the different facial expressions, and that heat map shows the features it considers to classify it as it does. So among our research contributions, first of all, we were able to overcome the black box nature of most models by implementing explainability. Then we carried out a smoother and smooth analysis on the data, as you see in the visualizations below. And then we were also able to train a new graph convolution neural network to map out spatial relationships among facial landmarks. So here this is an extended exploratory data analysis. First of all, this is a heat map. For these ones show the initial data before we carried out the smooth and smooth analysis, and then these ones, the ones on top are before, and the ones below are after we had tried to make them uniform. So here, from the ones on top, disgust is severely underrepresented and happy is overrepresented in both the testing and training datasets. Then, so after carrying out cleaning and then trying to and then the smooth and smooth analysis, our datasets were made uniform, where for testing we used 100 images in each class, and then for training we used 320 images. Yeah. And then finally, these are the links to our EDA code and our notebooks. Thank you very much.
My name is Bizimaana William Gad, a member of Group 7 Evening, and we're doing an explainable semantic graph convolutional network for facial microexpression detection. And Macro expressions are very minute facial movements that reveal underlying emotions in a brief moment. Our keywords were explainable AI. Then we had nodal embedding, micro expressions, graph convolution networks, DCNs, and machine learning. One computational problems were also that we came across where we had black box nature. There was also an imbalanced microexpression data sets. There was also complexity in extracting the spatial patterns. Our data set we used was the FER 2013 data set, which contained 35,887 grayscale facial images with resolution 48 by 48 pixels. The regional data set, however, had a number of disparities, including non-facial images, very unclear images, and some cartoon images. We therefore carried out data cleaning as a strategy to fine-tune the data set and improve accuracy of our models. Additionally, we realized that there were imbalances in data, specifically the discuss and happiness classes, is where we undersampled. We therefore carried out smart analysis. Our research objectives and questions were we had number objective was to build a convolutional network architecture that makes use of explainable mechanisms. Then number two was to build and evaluate a machine learning model that predicts concealable and minute facial expressions. And lastly was to train a graph convolutional network model on a well-established facial micro expression data set, employing appropriate loss functions and optimizers.
Thank you very much, Gad William and Ian, for the presentation. My name is Lusiba Collins, and I'm going to walk you through the code for the two models that had the best accuracy, and that is to say the Linet model and the ResNet 34 model. So as we can see in the first code cell, we imported all the necessary libraries that we need for our models, and then we went on to set up the directory for the dataset so that they are available for our notebook, and set up other configurations such as the epochs, which are the number of times our datasets will be passed through our models during training, the size of the images to be used, and then also the byte size, which refers to the number of images that would be used, that would be considered in a given iteration during training, in a given training iteration. Then we were able to implement the configurations for the various datasets, and then went on ahead to print the images to ensure that the dataset is available to our notebook. Then we prefetched our datasets so as training can commence immediately. And then we went on further to do image preprocessing, whereby we defined the size, the sizes of our images. And now we went on to define our Linet model first of all, which is a model inspired by a Chinese called Linet. And in this model, he was able to implement various neural network layers that are responsible for doing the extraction and then also the training of the various micro expressions, with a conv2D layer being responsible for extractions of the various features to represent the different micro expressions. Then we went on to define our ResNet 34 model, which is a variant of the residual network architecture, which employs a special layer called the residual layer. And these residual layers help to solve what we call the vanishing gradient problem, which is a problem that occurs when deep neural networks are used, most especially those networks that involve a lot of layers during training. such that during back propagation, when training is being done, certain layers are skipped to ensure that training is done faster and effectively. So we defined the first layer of the ResNet 34 architecture, which is the custom conv2D layer, responsible for extracting the features from a given image, and these features are passed on to the other layers to train the model and inform it that such and such features belong to such and such a micro expression. And that was our ResNet 34 model code. And then we went on to define the loss function, and then also the other metric that we shall use to assess the performance of our model is the accuracy of our model during training. So we first of all trained with a ResNet model, and as you can see, there was an improvement from the first epoch to the fourth epoch. There was a tremendous improvement, that is from 53% to about 81%. And as you can see, at the time taken was roughly 2 hours for each epoch. And this was one of the limitations we faced with the ResNet 34 model, despite the fact that it gave a better accuracy in a very limited number of epochs. The training time was a bit long, and so we're able to train for only 4 epochs due to the long training time. Then we went on to train with the lineate model, and with this model, since each epoch took a few seconds, we're able to train for 20 epochs. And as we can see, after the 20 epochs, we have an accuracy of 98%. Then we went on to draw our loss and accuracy plots for the two datasets, that is for the training dataset and validation dataset. And as you can see, for the training dataset, our loss continued to decrease as we trained more. And whereas for the accuracy, our accuracy went on to improve as we did more epochs. Then we're able to visualize predictions on the validation dataset, whereby we assessed the model that we have trained to see if it can accurately predict micro expressions in the validation dataset and see if there is correspondence within the validation dataset, and it did so for majority of the images, as we can see, and just a few that maybe were not able to correctly be predicted. We went ahead to draw a confusion matrix, as we can see, for the lineate model, which showed that our model at least performed quite well for our various micro expressions. Some of the limitations that we faced is that there was limited data sets, whereby it was only the SAM, the CASME2 datasets, and the FER 2013 datasets that were available, of which even the 3 datasets of poor quality. And then also it was very difficult to implement the explainable AI for graph convolutional networks, which was complex. And then also, since facial micro expressions are temporal in nature, it was very hard to implement them with graph convolutional networks, which capture better spatial dependencies. As we conclude this presentation, you have to note that micro expressions are very important expressions that detect more accurate and real emotions of a human being, as they tend to hide them. So it's very important to find ways of detecting these micro expressions that they can be used in the healthcare setting, with online therapy sessions to identify emotional disorders in patients and creating intelligent assistants. These are the references that we used for our literature review, and some of the models that we were able to implement were also inspired by the authors. Thank you.